Take it away, Mark.
Okay, brilliant. So I'm Mark Yoder. I did my doctorate in physics here at UC Davis, and my dissertation and research since then has focused on various aspects of natural hazards dynamics and earthquake predictability and earthquake forecasting. So it involves a lot of quantification of hazard and studying some fairly obscure isn't quite right, but a different approach to the earthquake problem. And for me, the real focus has been that I focus on earthquake sequences and earthquakes as sequences rather than earthquakes as individual events. Before I went to grad school, I worked with databases and did a lot of software development and database programming and things like that. Okay, I'm gonna load up my. I've got to find this this file real quick. This will just take me a second. Okay. So when I came into grad school, I definitely came in with a very kind of data-intensive perspective, and it wasn't for some years later that people started calling that data science. Okay, so I hope that's visible enough. It's a little bit. Okay, so yeah, so I definitely came into grad school with a kind of data-intensive approach. Before grad school, I worked, as I said, I was working with databases primarily in healthcare informatics. So we're doing various types of healthcare outcomes and web-based programs and back-end analytics and stuff like that. So I think with that, we'll go ahead and get started. And I know, I guess most people are kind of on mute, but if there's a mechanism whereby people can ask questions as we go, I'd be fine with that.
Mark, this is Bob again. I will watch the chat screen.
As I was putting together this
as questions come in, I'll keep track of them and keep a record of them for you, and then we can ask you at the end.
Okay. Yeah, that'll work. Okay, so we'll go ahead and get started. Okay, so okay, so right, so I'm working at UC Davis, but I also work with a couple of groups down at NASA JPL, and collectively speaking, we're all very involved in natural disaster science and natural disaster response efforts. So in addition to developing research-based research for earthquake predictability and earthquake forecasting, we end up getting involved in several earthquake disaster simulation scenarios, including the Great Shakeout and a couple of other that are put on by Department of Homeland Security in California and state of California. And we also ended up getting involved in the actual earthquake. So our first real test in a quasi-mature state was the Napa earthquake last year, and then we got involved a lot in this Nepal earthquake. And specifically from UC Davis, we provide them with earthquake forecasts and an interpretation of those, of course. The JPL and NASA teams in general provide an enormous amount of satellite data and computational resources. So for example, what you're seeing here on the cover slide is it's a surface deformation model based on observations from various satellite data, probably InSAR data, and then they use an algorithm that does an elastic media inversion to estimate the deformation and from the earthquake, and from that they can infer where we might find damage, where we might find landslides, et cetera, et cetera, et cetera. So we'll get going now on what I do primarily. So I'd like to have special thanks for my collaborators, the people I work with. My wife helped me put together some of these slides as well, and collaborators at UC Davis and JPL. So overview, the problem. I always start with stating the problem. Earthquakes are bad. Earthquakes kill people and they're expensive. So we're going to do a little bit of background. How do we describe earthquakes? What are, as we say in physics, what are the models of earthquakes? What are our objectives? Our objectives are to improve our ability to forecast earthquakes, improve our response to earthquake disasters, and to fundamentally better understand earthquakes. Those are the objectives of the research and the general work that we do here. The challenges are, well, this is going to be a little bit different from a data science perspective because one of our challenges, frankly, is limited data. Unobservable observables. We can't observe stress and chaos. Earthquakes are chaotic systems. Solutions. Well, one of the solutions we're going to talk about is earthquake simulators and new models. And again, it's sort of a physics thing. When we talk about new models, we're talking about new models of earthquakes, new statistical models of earthquake hazard, new ways to understand earthquakes and predict something about them. The products that we produce are forecasts, earthquake forecasts, and new science. And then we'll conclude a bit. So a good read, I've only read parts of it, but Tony Hayes' book, The Fourth Paradigm, and this is his take on, Tony Hayes, a very accomplished, I believe, cosmologist, works for Microsoft, et cetera, et cetera. He is trying to kind of explain the role of data science in physical science. And it's something that we're going to have to keep in mind during this talk because I'm mostly going to talk about the applications, and then I'm going to have to just try to put it in the context of the data science involved. So the fourth paradigm is this concept where long ago, as science, the first paradigm of science was observables and the scientific method, basically making objective observations. This is Aristotle and all the Greeks, that the stars moved and the planets moved differently, for example. The second paradigm is quantitative methods, calculus, closed-form solutions. That's Newton, Maxwell, etc. The third paradigm is computational and numerical methods. So now we can solve nonlinear problems. We don't need necessarily a closed-form solution. And this was a big deal for turbulence and problems like that. And the fourth paradigm is today, the data-intensive scientific discovery. And the way I like to phrase this in a sentence is that these are problems that fundamentally require multiple observations. And the analogy of the blind men observing the elephant is one that I borrow from Tony, I think. And the point is that all of these people, these blind people, they are observing the elephant by feeling it. But because an elephant is a big, complex thing, they're all feeling a different part of it. And if they don't understand that it's a big, complex thing, then they all draw very, very different conclusions about what an elephant is. An elephant's a snake. If you're grabbing its trunk, it's a tree. If you're grabbing its foot, it's a wall. If you're pressing against its side. And so these are the sorts of problems I think that we're seeing in physics today that we're able to address by taking a sort of data science approach to solving them. So, okay, so the problem. Earthquakes are bad. And we'll just represent that graphically and move on. We can talk about statistics and numbers. The Gorka earthquake in Nepal killed on the order of 10,000 people. The Tohoku earthquake, magnitude 9 earthquake in Japan in 2011 killed 20,000 people and caused at least $100 billion in damage. And a lot of people are putting that number at $1 trillion. And Japan is the best prepared, arguably, the best prepared country for earthquake hazard in the world. So if this can happen to Japan, it can happen to anyone. So before we get into the challenges and the rest of this, let's just talk about what's an earthquake. So going kind of back to the beginning, the Earth is built in, is arranged in layers, if you will. You've got the inner core, the outer core, the mantle, the lithosphere, or the crust. And what happens is heat from the core is trying to escape into space. So it's hot in the middle and it's cooling into space. And this process produces convection currents in the mantle. The mantle is semi-solid, but it's viscous, and so it moves and forms these very, very slow convection currents over large timescales. So it's solid in the sense that so is ice solid, but glaciers flow downhill like rivers. And so you form these convection currents in the mantle, and that pushes and pulls and tugs and twists on the crust or the lithosphere, and so the crust breaks and it moves around, and when it moves, it doesn't move gently. It sticks, it slips. And so it's the fracturing of the crust and it getting pushed around by these convective cells that results in earthquakes. And so we get different kinds of earthquakes. We get strike slip, normal, and reverse faulting. So strike slip is a twisting motion or a rotational motion. That's where two fault surfaces slide side by side. It's down there in the lower panes. Normal faulting is a pulling apart, and so it's where the crust gets pulled apart and one side drops down. And then reverse faulting is where the crust gets pushed together and one side gets pushed up. So basically every direction you can push, pull, and tug the crust, it'll break in that direction, and we get different kinds of earthquakes in that way. And then there's complexity, chaos, and unpredictability. So where does the unpredictability of earthquakes come from? Well, it comes from what in physics we call complexity, and it's also referred to as chaos. This is chaos theory. So this elastic rebound model we're talking about, where the Earth's crust gets pushed and pulled and twisted and then breaks. Well, so a segment of Earth's crust accumulates strain slowly, and then when it gets to a certain level of accumulated stress and strain, then it breaks, and then the process starts over. That process is actually quite predictable in isolation, but in real earthquake systems, these faults all interact with one another, and it becomes very complex. And so what you're looking at here, this figure, is a representation of the ALCAL2 fault model, which is based on the USGS USURF2, which USURF means, I believe, Uniform California Earthquake Rupture. I'm gonna say forecast, but fault model actually. So this is a running project in the USGS, and they produce sort of the standard fault model for California. And this is how we've implemented it in a virtual Quake simulator, which we're going to talk about in a bit. The virtual Quake simulator as represented in Google Earth. So you can see that this fault system is really complex. Some of the faults are long and straight, some are zigzagged, some are close to other faults, some are far away. And the result is that you get a very chaotic behavior. So this is the same kind of interactive phenomenon as you see in the stock market. The stock market in principle is very simple. If I think a stock is priced too low, I buy it. If I think it's priced too high, I sell it. And if there will be another buyer and seller on the other end of that transaction. But when there are a lot of us together, even with these very simple rules, we get a very complex, unpredictable behavior. And at the heart of this complex, predictable behavior is what we call 1/f noise, or power laws, and fat tail distributions. And these are basically names for the same thing in different disciplines. So what the 1/f noise basically means is that the amplitude of your noise is inversely proportional to the frequency. And so what happens is if I have a noisy signal, normally what I do is I increase my sampling, I sample more, I increase my data, the amount of data. I do more observations. But with 1/f systems, when you do that, you introduce more noise from the longer frequencies. And so you end up with basically having gained no signal. In financial systems, they talk a lot about fat tail distributions, and that's what this picture down below is. It's saying when processes are independent, we expect exponential distributions of large events. So a very, very large event is exponentially improbable compared to a smaller event. But in these complex systems, these power law or fat tail distributions, those probabilities of large events are much, much more likely. And so you see this in, you heard this in 2008 and 2009 about the stock market crash. The probability of this crash was very low. The expected interval between crashes of this magnitude is longer than the time of the universe, et cetera, et cetera. Well, that's assuming an exponential model. What they're really saying is that the model was wrong. And so this is a, this is nominally, this is a big part of data science itself, because this is a question of using the right statistical model to optimize your data or to optimize a process. And so one of the problems that the financial markets had was that they were using exponential and other models to optimize their trading algorithms or their risk assessments. And in fact, the correct model was this power law model. And so they were not properly accounting for the hazard of very, very large events. In earthquakes, we see these power laws primarily, well, we see them in the form of a lot of scaling relations, most notably Gutenberg-Richter scaling. What Gutenberg-Richter scaling says is that there are a lot of little earthquakes, but only a few big ones. So specifically, if I go back a slide, we have this power law relationship up at the top. The number of events greater than some magnitude m is, oh, I didn't write that correctly, is m to some exponent. Okay, so what's this saying? In earthquakes, the exponent is 1, and so the takeaway is that for every one magnitude 6 event, there are about 10 magnitude greater than 5 events, and 100 magnitude greater than 4 events, et cetera, et cetera. So one of the takeaways from this is that for practical purposes, there's no upper limit to earthquake magnitudes. Earthquakes get really big, and in fact, this is a general characteristic of natural hazards. Natural hazards are systems where arbitrarily large events can occur, and their frequency magnitude distribution is governed by these power law distributions rather than exponential distributions. Okay, so kind of taking a step back, our primary scientific objectives in this work are to forecast earthquakes, calculate earthquake probabilities. This comes in two forms: long-term independent, time-independent models, and short or medium-term time-dependent models. We want to develop science technology to respond to earthquake disasters, and we want to, in general, use this science to understand earthquake physics and determinism in earthquake systems. The data that we have to work with, well, there's a bunch of data we can work with. The most common data we work with are seismographic data. So seismographs are instruments that detect when the earth shakes. And seismology is a very, very well-developed field, and I leave it primarily to seismologists. With seismographic data, the magnitude, locations, and other data from point-like data from earthquakes are actually quite well understood, and the solutions are pretty good. We have high-quality networks in California, Japan, and other developed areas, and we have very good solutions for m greater than 5, magnitude greater than 5 earthquakes on a global basis. And that's basically because magnitude greater than 5 earthquakes are big enough for the global network to see them. Pretty much every decent seismometer in the world sees a magnitude 5 earthquake somewhere else in the world. So what we have is there are a few sources of data. They're reduced data, and they're pretty easy to work with. We have good data for about 20 to 30 years in California, and probably similarly in Japan, although they keep their catalog a little bit closer to themselves. Paleo-seismology. So this is the study of ancient earthquakes. This is where people go out and they dig up an old rupture and estimate what the magnitude of the event was and when it happened, et cetera, et cetera. But the bottom line is that those data are incomplete, imprecise, and there's a lot of things we don't know about them. Most fundamentally, we don't even know if the fault system at the time of that earthquake represents fault conditions that represents the fault system today. GPS data, they're great. They're very accurate. They're very high-resolution time series data. One limitation not listed here that I think of now is that they only show surface deformation. They don't directly show any deformation at depth. We can invert for that. GPS data are relatively sparse wherever we put a GPS station. And so typically in a really good area, we're talking about something on the order of 1 kilometer. GPS data are available since about 1990 in some places, and the network is growing. Remote sensing, well, this is a new technology we're going to see a little bit of. Pre- and post-seismic surface deformation, so that's what we can observe, pre- and post-seismic surface deformation. Remote sensing tend to have very high resolution. So the remote sensing data of most significant interest for earthquake science is InSAR, which is interferometric synthetic aperture radar. So it's a radar-based technology. And well, we won't go into the details of how the waveform radar works. From the data science perspective, very high resolution, pixels on the order of 10 meters, and change resolution on the order of 1 centimeter. InSAR is either flown on a satellite, like the ALOS-2 satellite, or flown on an aircraft, like the JPL UAVSAR program. And so the areas that are covered would be on the order of hundreds or maybe 1,000 square kilometers per pass. The temporal resolution of these data is whatever you do with it. If you've got a satellite, it's whatever its orbital periodicity is, so it'll be daily to weekly or so. And for airborne, obviously, it's on demand. It's whenever you fly your aircraft. JPL has a growing UAVSAR, which is an airborne InSAR technology program, and they're starting to get a pretty good collection of data sets. And so we're really looking forward to doing some interesting science with it. As far as the data volume go, these are relatively big. This is where we started getting into some big data problems, where the files they're fairly large, on order of gigabyte per strip. And in the big data world, maybe that doesn't sound like a lot, but the processing on these is pretty intensive. So there's a lot of CPU cycles per gigabyte, and in general, it starts to transform it from a desktop problem to something else potentially. So, and we're still into some background here. So so we want to do is we want to forecast earthquakes. We want to mitigate hazard. In the end, this is our objective. We want to mitigate hazard. We want to reduce losses and save lives. So standard hazard mitigation models are pretty straightforward. What you do is you estimate the mean rate of large destructive events, or the probability of a large destructive event, like a magnitude greater than 7 earthquake, a category 3 hurricane, or something like that. And what you do is you build up your infrastructure to withstand that event. So, for example, cities in Florida and the South tend to build to withstand, say, a magnitude or a category 3 hurricane. And the idea is that if a storm bigger than that is coming, more hazardous than that, then you evacuate. And this works really well for hurricanes. It works well for wildfires and other hazards because we can see them coming. We know when a hurricane is going to happen based on meteorological observations, and we can track it and watch it happen using satellites. Even before satellites, we could do a relatively good job of tracking hurricanes based on mariners' reports and meteorological measurements, et cetera, et cetera, et cetera. But this doesn't apply very well to earthquakes. Earthquakes are fundamentally very difficult to predict. So we tend to know where earthquakes happen. Earthquakes occur on known faults, and this is a chicken and egg question. People will say, oh, well, earthquakes occur here because there are faults. But you can also say that there are faults because earthquakes have occurred there. But in any case, where we see faults, we expect earthquakes. And that works pretty well, actually. When? We don't know when they're going to happen. That's the fundamental challenge, is the temporal predictability. The duration. Well, a magnitude 7 earthquake lasts about 60 seconds. And observations. We cannot directly measure tectonic stress or track earthquakes by satellite. So let's put this in context compared to a hurricane. Well, so a hurricane, we know it's coming because we can measure the drop in barometric pressure, and we can watch it form from satellites. So we can directly observe its formation. Forest fires, we know when they start, and we can directly observe their progress from ground-based units and also from airborne and satellite-based units. So we got a pretty good idea of say, when those hazards are going to happen in the first place. And when they do occur, we can watch them evolve, and we can track them. Moreover, a hurricane lasts several days, so it's sort of a long, drawn-out disaster. Earthquakes, we don't know when they're going to happen, and when they happen all at once. So again, Haiti, magnitude 7 earthquake, 60 seconds later, Port-au-Prince is destroyed. The Tohoku earthquake, magnitude 9 earthquake, lasted for 6 minutes. Now, and then there was a tsunami that followed. So earthquakes are hard to predict, and they're hard to contend with. We don't know when they're going to happen, and when they happen all at once. So going back to the data that we have and this general problem, even given the best scenario, the time scales of the data available, while large earthquakes have recurrence intervals on the order of hundreds of years or thousands of years or even 10,000s of years. Okay, our paleo earthquake catalogs, okay, so arguably they have time scales that are compatible with that, but they're just very incomplete and imprecise. Seismographic data we have for the last 30 to 100 years. GPS data the last 10 to 30 years, and remote sensing is all brand new. We've maybe got 10 or 20 years of remote sensing data, and 5 years that's particularly useful. So one of our fundamental problems, besides the fact that earthquakes are very difficult to observe directly, is that even if we knew how to do it, the data that we have are incompatible with the timescales of the hazard of the events. And so how can data science help? Okay, so our challenges are we have limited data, we have unobservable observables, chaos and complexity. So this means that a lot of our standard statistical models aren't going to apply very well. And that brings us to our last point, our current scientific models up to the task. And so again, what can data science do to help us? Well, we need to use smart techniques to do more with less data. And so some of that is going to come in the forms of pattern recognition algorithms, trend analysis, and different methods of partitioning data, all of these to resolve some sort of signal. But to resolve that signal, we need new models. Nominally speaking, we've got the wrong models. We're looking for the wrong signals. And so we need new physical models of earthquake processes, and we need new statistical models of these processes and metrics and statistical metrics of how to measure when we're in times of elevated hazard and mitigated hazard. And third, we need to generate new data sources. So we need to expand seismographic networks, GPS networks, etc. We need to develop remote sensing. And another source that we're going to talk about next is simulators. We can generate data using simulators. And the last thing we need to do is we need to figure out the right way to combine and convolve these data from multiple sources. So what we have is we have a lot of data of different types from different sources that are telling a different version of the same story. So what we need to understand those data, and then we need to put them into algorithms that answer the same question. So, and a point of clarification, it's not the source, it's the science. We've looked at lots of different kinds of data. So there's a big controversy in this business, and when we say where there are a lot of people that just say fundamentally earthquakes are not predictable. Okay, so we've looked at lots of different kinds of data, and yet earthquakes still remain unpredictable, for now. We've looked at lots of different kinds of data, including slip along faults, looking for patterns in earthquake magnitudes, patterns in earthquake locations, et cetera, et cetera, et cetera. And what the big story ends up being when you speak with colleagues in this business is say, now we've looked at all the different kinds of data, and we haven't found a precursor, we haven't found a signal. Well, complex problems require complex data. And so maybe it's not that we're looking at the wrong data, we're just not looking at the data the right way. And so a lot of this, just from a kind of political perspective, comes from the Parkfield region of the San Andreas Fault, where a magnitude 6 earthquake occurs approximately every 24 years in a very quasi-periodic kind of way. What happened was a couple of groups put together this big experiment and announced a prediction of the next Parkfield earthquake back in the 80s. And the problem was that it just didn't happen. The earthquake was supposed to happen in the late 80s or so, and it didn't happen until 2004. And the basic conclusion was that there was no precursor signal, and that earthquake predictability just simply cannot be done. But there's some more recent literature, and I contend that the problem, the conclusion is premature, and that the problem can potentially be solved not by looking at a different kind of data, but looking at the data differently. Now, that does include looking at different kinds of data. It includes looking at InSAR data, GPS data in combination with seismographic data. But fundamentally, the idea is to look at the data differently, to paint a different kind of picture. Okay, so let's start with a simple forecasting metric. The simplest forecasting metric is the recurrence interval between large earthquakes. So all we want to know is what's the average time interval between magnitude greater than 7 earthquakes. As simple as that. Well, okay, so what's the problem? Well, in Southern California, there have been 3 in the last 100 years, and they all occurred in the last 18 years. So we really can't calculate a meaningful mean rate. So in other words, if we're looking to plan for magnitude greater than 7 earthquakes in Southern California, we're looking to establish infrastructure codes, et cetera, we want to know how frequently they're going to happen. And we don't have enough data to directly calculate that. There are 3 events, the Landers in 1992, Hector Mine in 1999, and El Maricucupan 2010. So we can't directly calculate a mean rate from these data. So there are options. The most common approach to solving the problem is to use fault-based models and come up with some scheme to calculate the probability of every possible earthquake on the fault on the fault system. And there are people still pursuing this approach, and there's a lot of good science that comes out of it. But all in all, it's a relatively unconstrained and impractical approach. There are other things you can do. You can extrapolate the rates of large earthquakes from the rates of small earthquakes based on the Gutenberg-Richter statistics, and we do that. But another approach is to use simulators to produce synthetic catalogs. So the figure on the right is I think 5,000 years of seismicity from a catalog produced using the virtual Quake earthquake simulator. And the contours just show where seismicity is the most active. So this is an approach. This is an approach that we take in this group. This is a lot of our research. We call the virtual Quake simulator, and it was formerly known as Virtual California, but we've generalized it so it can take different fault models and things like that. So it is a fault-type physics-based earthquake simulator. That means our earthquakes occur on discrete faults, and we use physics rather than purely statistical models to figure out where earthquakes are going to happen. It's what we call a half-space boundary element. So you can see this picture where the fault model is discretized into little 3-kilometer blocks. And what we do is we have this half-space model of a fault where one side is, well, basically where we only model one side of the fault. So one side of the fault is these blocks, and these blocks slip against the other side of the fault, which we just sort of treat as an amorphous mass. And we do this for the very simple reason that it makes the problem computationally tractable. And this is, again, where we get into some data science and some computer science. The USURF2 fault model of California at 3 kilometers is something on the order of 14,000 elements. And again, that doesn't sound like a lot maybe in the data science world, except that this is a computationally intensive process. So for example, to run all of California for 10,000 years on an i7 3 gigahertz machine takes about 3 days. So we have a lot of flops per block element. We have a lot of computational flops per gigabyte that we produce. So the basic model is that the elements in the faults gradually accumulate stress and strain, and at some threshold they break and they distribute stress to their neighbors. By the way, too, the simulator is all open source code. You can get it on GitHub. You can get it from this geodynamics.org, which is an NSF program that's run out of UC Davis. And community contributions and collaborations are very much encouraged. So we get a lot of data out of virtual Quake, and we'll just use an example of some of the data that we produce, or some of the reports that we produce. So most of the work right now, we're focusing on a 50,000-year simulation that we ran a couple of years ago. There are 2,000, so compared to California's actual history of 3 earthquakes, we have 2,028 magnitude greater than 7 earthquakes. And we can calculate the mean recurrence interval on that fault system to be about 24.5 years, plus or minus about 6 months. We, in addition to the mean interval, we can calculate the distribution of intervals, and we use a Weibull distribution, and we won't get into the details of that. The basic outcome of these figures, though, so what we do is we show the probability on the top figure, the probability of a recurrence interval being greater than some delta t, given the fact that we've already seen some t naught since the last earthquake. So in other words, what's the probability of a 24-year recurrence interval 1 day after an earthquake just happened, or a 24-year recurrence interval 10 years immediately after the last, or 10 years after the last earthquake? What we find is for the Southern California system, it doesn't change much. It's basically Poissonian. The lower plot shows the expected time to the next large earthquake since the last earthquake, and you can see for the very first part of it, it's just flat. So we're basically getting a Poissonian model back. But we take another look at it. So here's some new science, and again, we discover this new science not by making a single observation, but by altering the way we look at our data. So in this case, what we do is we partition the data. We partition the data by independent rupture sources, and in this case, that we more or less define that as a fault segment. So if we look at 2 specific fault segments shown in the arrows here, and we run the same analyses and look at their interrecurrence intervals and their waiting times, we find that for fault segment 111, which is here I'll go back, which is this upper one in this crowded group of faults, compared to fault, I think it was 123 we're going to do down in the lower part, out down by the El Mayor-Cucapa earthquake. We find that these systems behave very differently. Okay, so for segment 111, the random Weibull theory overpredicts the rate of large earthquakes, and for 123, it underpredicts the rate of large earthquakes. And if we look at the waiting time distributions, this is even more interesting, I think, because on the right, what we see is what we classically expect from earthquakes. Right after a big earthquake, so in other words, time since last m greater than 7 event is 0, we expect the next earthquake to be a long ways off, and then we expect it to gradually accumulate stress, and that time to the next earthquake gets shorter and shorter and shorter, and then fail. So that's what we see on the right, and that's what the classic picture tells us to expect. But when we look on the left, the shortest intervals are actually immediately after the large earthquake. So in other words, these earthquakes happen in clusters. These earthquakes, maybe they're triggered, we don't really know. But we get this fundamentally different kind of behavior, and we discover it not based on looking at a different kind of data or looking at a new type of measurement We discover it by looking at the data a different way. We discover it by partitioning the data so that we can resolve this phenomenon. So we can take this a step farther. Is there evidence of deterministic behavior in there? Well, I'm not actually sure. I think you can actually answer that question from the plots above. But what we mostly show in those two figures above is that there's different clustering. And we can get into a discussion of whether that implies deterministic behavior or just different clustering. But we can also address it directly. So there's a hypothesized phenomenon that is very controversial called pre-seismic acceleration, or that's what I call it. And this is just the notion that the rate of earthquakes, of small earthquakes, before a large earthquake increases. And this is in symmetry to aftershocks, where, and we're going to talk about it in a little bit, I think, where everybody knows, everybody's been in an earthquake knows that immediately after an earthquake, there are lots of smaller, hopefully, smaller earthquakes. And those are called aftershocks, and the rate of those decreases over time. Well, again, the notion is that before the big earthquake, there should be this symmetric process where the rate increases. This is predicted and observed in rock fracture experiments and rock fault and faulting theories, and it's easy to produce in the lab, but it's very, very difficult to isolate in nature because of the 1/f, the scale invariant, the chaotic behavior of earthquakes. So what we're going to do is use the simulator, because in the simulator we can do anything we want with our data. So we're going to consider simulated earthquakes on individual fault segments, and we're going to fit the local interoccurrence intervals, which is the inverse of the rate, over some number n of events. And if the slope of the line, in other words, the change in the rate or the change in the interval, is decreasing and indicating increasing rate, then we're going to issue an alert. If the slope of the line is greater than that rate, in other words, indicating that the rate of earthquakes is slowing down, or a large earthquake occurs, we'll cancel the alert. So this is a simple model. It's been done before, but it hasn't been done in the simulator, and it hasn't shown a result like this. So what we run this algorithm, and what we see is that it does a pretty good job of identifying when the large earthquakes are going to happen. So in the simulator, small groups of earthquakes occur at an increasing rate before the large earthquake. And this isn't something that's built into the simulator. This evolves from the behavior. And so if we can assume that the simulator is a pretty good simulator of real earthquakes, then we can hope, then maybe we can figure out a way to partition the earthquake data to observe the same phenomenon. And so in this example here, and this works on all the fault systems, which I'm going to show in just a second, in this example here, which is a small snapshot of the full simulation, 7 of 9 large earthquakes are predicted. Well, we want to quantify that, and here we're getting, again, some data science, because what we need is a metric that we can give to a computer to optimize an algorithm. So we want to quantify that, and in this case, as an example, we just use a receiver operating characteristic, or ROC metric. And so the basics of ROC is you have a contingency table, and you have earthquakes, events that were observed and predicted, that would be A, so that's a hit, or observed and not predicted, that's a miss, or observed, not observed and predicted, that's a false alarm, or observed, not observed and not predicted, in other words, a correctly predicted non-occurrence. And we have the hit rate, which amounts to the H, which is, as you can see on the slide, A over A plus C, is basically the hit rate is the percent of correctly predicted events, and the false alarm rate is the percent is the rate of false alarms. And in this case, for the false alarm rate, what I use is the total time during which alerts were issued, and the hit rate is the number of earthquakes that occurred during alerts. So we get a percentage of earthquakes that were predicted, the hit rate, and a percentage of time under which the alert was issued. And we want the hit rate to get big and the false alarm rate to get small. And so we can come up with just a score. A good score is really straightforward, H minus F, so the hit rate minus the false alarm rate. And we can plot the hit rate, the hit rate as a function of the false alarm rate. That's what you see in the lower figure. And basically, everything above the red line, where H equals F, everything above that red line indicates information gain. And so we show two clusters. One is where I use just the simplest default guess at where our parameters N and B should be. And the other is where I use a Monte Carlo or a random guessing algorithm, and I sample the N and B naught space to get the best H minus F performance for each fault segment. And you can see from this that in that context, every single fault segment produces an information gain, and most of them produce a very significant information gain. So there are lots of different kinds of earthquake forecasts. The USGS has various hazard maps. There's a group that is affiliated with my advisor here, openhazards.com. They produce a global and California and higher resolution earthquake forecast every night. This earthquake forecast is basically based on Gutenberg Richter scaling, and it basically says, well, we've seen a lot of little earthquakes, but not enough big earthquakes, or too many big earthquakes. And based on that, it calculates a rate and probability of more earthquakes. Another area of interest is aftershock forecasting, and this is where I've done a lot of work. So we're going to try to move quickly through this. Basically, aftershocks are the earthquakes that come after earthquakes. And one way of describing what an earthquake really is it's the moment when the rate of earthquakes, the local rate of earthquakes gets really, really high. There's usually one really big earthquake in that group, and then the rate declines, basically like 1 over T. And so you have this Omori relationship where the rate of earthquakes after a big earthquake declines like 1 over T. And you can do the same thing for the spatial distribution, and you can say, well, the distribution, the density of earthquakes basically declines like 1 over R from the main shock. And so we're back to this elephant analogy of elephants and earthquakes. So earthquakes are not point-like. Earthquakes have finite rupture length, they have finite duration, they occur in sequences, and we can use these properties to constrain aftershock rates. So here's what we're doing here's a case where, from a data science perspective, in the earlier slides we were using a statistical constraint or a statistical optimization on our data. Here we're going to start with we're going to use a physics-based constraint. So if I go back here briefly, we have this Omori rate, this 1 over tau T naught P plus T to the P. Those parameters, tau, T naught, and P, those are all tuning parameters. And so if we want to know what the rate of aftershocks is after a large earthquake, we have to find the right values of those numbers. So one way to do that is to take a bunch of earthquakes and just throw CPU at it and try to optimize them outright. And I can tell you that I tried that out as a matter of principle, and it just doesn't work very well. And so it ends up being a very subjective problem. And so instead what I did is I introduced a constraint. I introduced constraints based on the physics of the earthquakes, the physics of the rupture length and the rupture duration. I come up with a core model, and then what I do is I take that core model, and this core model basically predicts the rate of aftershocks immediately following a large earthquake, and I plug it into a framework where I give it a big catalog, say a 5-year catalog, or I give it a synthetic catalog. I plug that into my aftershock model. I do a bunch of computational plumbing, and I can come up with a map of expected aftershock rates. So the map shown here is actually the map that we deploy to the Napa earthquake response organizations. We did the same thing in Nepal. And so, for example, here, so this model is good for two things. One, it's good for just visualizing seismicity. So here are the earthquakes that basically have occurred since the large M=7.8 Gorka earthquake in Nepal. Here are the earthquakes just plotted in space. But if we apply this aftershock forecast, in addition to actually giving a quantitative or semi-quantitative forecast of the aftershock rates, it's just a better visualization of the seismicity. So what this tells us, compared to the one before it, it says, okay, well, there's earthquakes all over the place here, but these ones over to the east, these earthquakes to the east, they happened more recently. The bigger, more recent earthquakes happened on the east side of this distribution, and the expected rate of aftershock seismicity is going to be concentrated there. And in fact, this is the forecast that we put out on May 7th for the Gorka earthquake. And you can see there's a big old hotspot down in the lower right-hand corner, and that's exactly where the magnitude 7.3 aftershock happened on May 12th. So we were actually pretty pleased with the performance of this one. Okay, so modern earthquake response, and here we are just kind of wrapping up. Bottom line is that earthquake and disaster response today is using a lot more satellite data, a lot more computational infrastructure. It's much more data intensive and computational intensive than it's ever been. Tohoku, Napa, Nepal, and numerous simulated exercises have demonstrated this. And I want to make the point too that we keep getting better at these things every time we do an exercise. So what we're doing is we're directing research to produce, distribute, and convolve these resources. So what we really want to do is, for example, we want to convolve our aftershock forecast map with landslide hazard models and produce landslide forecast maps. And that's actually a big area of study and interest right now. There are several pending science and other prestigious publications, so I'm a little bit limited in what I can talk about there and what figures I can show. Here's another example. This is a damage proxy map that was put together using, I think, primarily InSAR data, largely from the ARIA group out of NASA and JPL. And basically what they do is they use the InSAR data to find places where there have been significant changes in the digital elevation model before and after a large earthquake, and they infer that implies damage. And where those places correspond with cities and populated areas, then we infer that that's damage to buildings. We can also use it to detect landslide damage. In general, geodetics is the next generation of seismology. So again, instead of taking this point-like picture of here is an earthquake and this is its magnitude, we want to paint a picture of it. We want to paint a picture of how the Earth is deforming around that object, and then we want to take around that rupture, and then we want to convolve that with other data, infrastructure maps, and other geohazards, etc. So concluding remarks: earthquakes are bad. Data challenges, they run the gamut: big data, small data, incomplete data, noisy data. Physics challenge, chaos, unobservable observables. That's basically our data challenge as well. The solutions, they're coming from a lot of different directions: simulators, new physics models, new statistical models, new analyses. Disaster response. Disaster response is incorporating newer, bigger, better data sets and new computational technologies, and it's kind of an exciting place to be working right now. And then geodetics, in the next 10 years, we're going to be looking at the Earth in just fundamentally different ways. So that's what I've got.
Okay, Mark, this is Bob Bleicher. Mark, that was great. It was fascinating and perfect timing. We're out of time. I do have one quick question I wanted to ask you.
Yeah.
What were the tools and technologies you used in doing this, your work?
Yeah, the tools, technologies. Yeah, so we write most of our own software. It's very Python intensive. The virtual Quake simulator is written in C++. The analytical tools are primarily in Python, and we use C++ Python extensions a lot. I believe I can't speak directly for the other NASA groups. The JPL groups that I do work with the Quake sim groups, the Geo Gateway groups. Primarily, we write our own software, and we're really looking. I think some of us, anyway, are really looking at where and how to integrate some of these new data science technologies. But the truth is that, to a certain degree, a lot of them really don't apply to what we do. And one more comment is that academic and research science is funny in the sense that you don't usually have the luxury of building up a big computational infrastructure. You don't have the luxury of building up a data center that you're on a 5-year grant. And when that grant runs out, it's difficult to say, if you have hardware or a hardware-based system, it's difficult to say what's going to happen to it.
Okay, thanks. And it is 1 o'clock. Our time's up. If anybody has other questions or comments, you can go to the LinkedIn group, DataSci Pros, and